Okay, it looks like we're not getting any more people in, so I'll go ahead. So, as I said, it's my great pleasure to introduce Tom for this COMET webinar this month. Tom is a senior lecturer in volcanology at the University of Sheffield currently, although I gather from your past reading your online bio, you've travelled around a bit. So it was at Reading for your bachelor's, Lancaster for your master's, and then finally Sheffield for your PhD, if I've got all that correct. So that's where you are currently now. So Tom is really interested in using particularly low-cost sensors to investigate volcanic degassing processes, as well as some lab and modeling approaches. But I think the aim today, or the main focus today, has been on low-cost UV cameras for looking at volcanic degassing. So without further ado, Tom, please take over. Oh, sorry, one last thing. Any questions you have, please pop them in the Q&A. We'll get those answered at the end. And I think that's everything I have to say. So yes, now without further ado, please take it away, Tom.
Amazing. Thank you so much. Thanks for inviting me, Ben, and organising everything, Jin. So if you're watching live, hello. If you're watching later on YouTube, I hope you kind of get something out of this, and really happy to hear from anyone who has any questions about anything I talk about today. So really I wanted to reflect on UV camera usage. Particularly, I've used them now for over 10 years in a variety of locations, developed the instrumentation. And what I want to talk about today is kind of combined reflection on their value in comparison to other gas monitoring techniques, but also some of the work we've been doing at Sheffield to try and hopefully increase access to these UV cameras. So a bit of a journey today. Some of you may have seen some of this before if you've seen some of my previous talks, but hopefully I've expanded it quite a bit to include some more of the detail. So without further ado, I'll cover a few key points here and a few key case studies. So I really want to cover why low-cost instrumentation, why UV, and particularly permanent UV cameras, how we've developed our UV cameras here at Sheffield, based around the Raspberry Pi, a little bit about where our cameras are installed, and then some specific case studies where I really hope to kind of demonstrate some of the issues we've had with UV cameras, but also some of the real benefits, leading into a reflection on the future, on where I think UV cameras could and should take us in the future. So I'll kick off then with why low-cost instrumentation. So as scientists, I'm sure you've been in those situations where you really want to answer this amazing scientific question. You contact the company who sells the kit, and it's tens of thousands of pounds, and you think, well, that's, I can't afford that. You put it in the grant, and you've got a 5% chance of making that grant. And a lot of what I'm talking about today comes from that experience 12 to 15 years ago now, where we wanted to use these bits of kit, but we just couldn't afford it. So this gives us kind of the why of low-cost instrumentation. There's a real benefit in that it can widen access to instrumentation. So previously very high cost, inaccessible measurements, even with particularly large budgets in the UK by kind of comparison, it makes them more accessible. And by having low-cost instrumentation, it means it's easier to install larger distributed spatial networks for doing some really nice big studies. And some of the instrumentation I put here on the right-hand side, the Raspberry Pi, the Arduino, microcontrollers, microcomputers, which have really enabled this instrumentation to be produced. And an example of one of the bits of kit is the Raspberry Shake and Boom. Is a kind of a low-cost instrument for looking at a seismometer. It's equivalent of seismometer, so seismic signals and infrasound signals. And these kind of bits of kit can be really useful because volcanoes tend to destroy kit regularly. They're very hostile environments. And by making things accessible, almost plug and play, really easy to code in coding languages like Python, all of a sudden these bits of kit become accessible to a far larger user base. However, that also comes with its disadvantages. Sensors and instrumentation can often be built by non-experts, introducing potential errors in code or construction. And that can mean that multiple groups are making the same bit of kit in lots of different ways, and that can lead to intercomparison between data sets, a bit more challenging. So that can then link also with the sensors and data used themselves. They often have higher errors. And the question that you'd need to answer as part of that is that an error I'm happy with? Can I still get the usable scientific information to do it? You also then have the long-term suitability. Lower cost often, but not always, means that it might be more difficult to maintain over the longer time frame, particularly if you want to install things in a permanent setting. So it's a balance. I fall on the benefits of low-cost instrumentation, not as a replacement, but as an addition to a really nice value added to other bits of instrumentation, higher cost instrumentation. But I'm particularly interested in the gas side of things, and gas instrumentation can be exceptionally expensive, and it's often installed in the most dangerous and corrosive locations. So here's some work I did a while back now over Stromboli, looking at multiple vents. And that was only really enabled by low-cost UV cameras that we could distribute round the system to image all vents simultaneously and independently, while a drone flew through the plume to get these measurements. So that was enabled by the low cost of the instrument and gave a real benefit for the spatial science. So Stromboli is a really interesting location with vents that have different quantities of gas, different styles of behavior coming from each vent. So having a spatial idea about what's being emitted, what style is, and can give you a real insight into shallow plumbing systems and potentially how that system kind of manages itself over the long term with gas flow pathways and things like that. So gas instrumentation, which is low cost, replaceable, quick and easy to construct, and repeatable to construct, would be incredibly valuable and is incredibly valuable, I should say, for the community. So I'm thinking here about, the traditional remote sensing techniques, UV cameras, spectroscopy techniques such as DOAS, differential optical absorption spectroscopy, where you typically scan below plumes, but also the ones where you're really in the gas and you're sampling that gas to work out things like ratios. So that's why low-cost gas instrumentation. But why UV cameras then? So UV cameras are a really nice way of looking at your data because you can see it. You can see the imagery, and we'll see a lot in this presentation. All of the data you need is usually constrained within that UV camera system. So you can image your plume, you can have a co-aligned spectrometer to calibrate that image, and it's all within that camera system. You can work out plume speeds from the imagery. You can correct for background effects and even correct light dilution issues, as we'll see later on in the presentation. So UV cameras can be really useful for that. And UV cameras are kind of I don't want to put DOAS versus UV cameras because I don't think that's the right way of phrasing it. They're a complement to and a different way of measuring sulfur dioxide emissions at volcanoes. So DOAS is the previously mentioned optical absorption spectroscopy, often installed below plumes, where the DOAS instrument scans below the plume to build out a picture of the plume profile. You then multiply that by plume speed. Now, traditionally, that can give you a data point every 5 to 15 minutes, depending on conditions, whereas a UV camera can give you a data point every couple seconds. So there are kind of benefits in spatial resolution with UV cameras compared to the DOAS. But in my view, I might be wrong about this, but the DOAS instruments have been used for quite a long time and they're very well trusted by the community. So sometimes there can be a little bit of reticence to adopt new techniques. And the simpling and the processing is a bit simpler with the DOAS instruments comparatively with the UV cameras. So of course, both of these systems have their issues, and I'm not going to get into too much of a comparison for or against either. I think they're both really good and they both work in complement. And hopefully a couple of the examples I show will demonstrate that. What I want to talk about is the real value of UV camera measurements for small scale spatial studies, but also long-term studies. And the group out of Palermo in Sicily have really demonstrated the high value of UV camera usage over long time frames. So Stromboli and Etna, here are two example studies. There are a few more. They're looking at changes in patterns of gas release between eruptions. They're looking at different emissions between different vents and switching between different vents. And this is real long-term valuable data series that you can then compare with other high time resolution streams. In this instance, tremor in both locations, and sometimes thermal output as well. So with a high resolution gas data set, you can then start comparing those with high resolution geophysical data sets. So that's a key benefit of the UV camera. The one key benefit of the permanent camera system, as opposed to campaign measurements, is that in challenging to measure conditions like this data here from Cotopaxi in Ecuador, if you've got this camera system operating permanently, and this is a 310 nanometer image where SO2 absorbs, you capture data when you can. And you can see illustrated quite nicely in this video that after a certain point of time, this plume looks amazing. You can see that darkening associated with the absorption of SO2 in the plume here, but then the clouds come in. So by installing these systems permanently, when there is good data, you get that data. And this is particularly challenging in humid, cloudy locations such as Ecuador. And this is an example here of an SO2 image where we have background area in that black box in the corner. And also we have the integration lines where that plume is crossing. The green arrows indicate the plume speed, determined using optical flow algorithms. And the spectrometer is pointing somewhere in this plume to build up a calibration profile. And the red here is the darkening of related to the SO2. So permanent cameras here give us all of the information we need to be able to derive these SO2 emissions when we have the data available. So what we've done at Sheffield is we've built our own, and that's quite simply because a commercially available UV camera system can cost tens of thousands of pounds, which is completely unfeasible, particularly if you want to install lots around a particular volcano, and you generally don't have the budget to do that. So the way we did this with our UV cameras is we use the Raspberry Pi architecture. We use the Raspberry Pi camera. And what we do is we remove some of the layers of these essentially mobile phone sensors to increase the UV sensitivity. And this is what this graphic shows here. Just get a pointer up. Where we have the Bayer array and micro lenses, and the Bayer array converts the light incident on the sensor into red, green, blue values, which is useful for true color images. But if we are interested in measuring UV light in one specific wavelength or two specific wavelengths, we don't need that. We just need the intensities of the light. So we can strip this, and by stripping this, we increase the sensitivity to UV light, which is what this image on the right hand side shows. And this is work that Tom Wilkes did in way back in 2015, 2016. And this image on the right hand side just illustrates how we do this. This is just scratched off. The darker areas are where the bilayer is still intact, and the lighter areas are where it's been completely removed. And this sensor here is the clean version of that. So we can do this with mobile phone sensors, and the sensor itself costs about 20. Things increase in price a little bit when you start packaging lenses and putting everything into a UV camera system. but the cost is still remarkably different from the original commercial system. What we then did is then compared this side by side with, at the time, a commercial JAI system. The PiCam is on the top and the JAI commercial system is on the bottom. The initial difference was an increase in resolution, but I'm sure you can kind of see that visibly there's very little difference between the two. So what you then do is you then take this data, you convert it into an emission rate trace, and the red trace here is the JAI commercial system. The black trace is our PiCam system, and this here is the scatter plot showing the relationship between the two. And you can see that it's near on identical between the two, with a very strong relationship. So that's great. Our low-cost system does exactly what the commercial system does, which means we can do what others can do for far lower costs. It means we make the instrumentation far more accessible. What we also have alongside this is a user-friendly open source GUI. So GUI is graphical user interface, which incorporates a really kind of rigorous set of processing protocols for UV camera data to give us your end outputs, and that's all available online. It's called PiCam Permanent, and this is the kind of trace you'll get at the end. This is actually from I think it's from Cotopaxi. If I recall correctly, you get different plume speed, emission rate options, and you can really nicely see the patterns associated with that, almost certainly atmospheric pulsing and mixing associated with this system. This is over the course of about just over an hour, and it really illustrates this high time resolution data set you can derive from UV camera data. And we'll see some comparisons with other techniques in a little bit. So we've now been pretty successful, and I must say that there are so many collaborators, and they were mentioned at the front title screen here, who have really enabled this and have kind of joined us for the journey. We've got 6 installed permanently. One is on a rainy season holiday / it's been partially eaten by some animals. So hoping to fix that soon. That's Kīlauea. And we've also got one coming online, hopefully in Turrialba sometime in August. So this has really been enabled by this low-cost approach, allowing people to install it quickly and affordably, but also with the reassurance that they're getting scientific quality data at the same time. So I'll talk through some of these now. So starting off with Merapi. So Merapi probably doesn't need too much introduction. Here's Merapi and gas plume coming from the summit area here. At the time we were measuring, it was pretty low activity, domes and some rock avalanches down the side. Here's the camera system. So this was funded by Royal Society International Exchange. The group came over here, learned how to kind of maintain the instrument, process data. They went back and installed this, and this is a really rigorous approach with a covered camera system, powered with mains electricity, and directly hooked up to the camera in this particular observatory here at Juraka. And you can see the volcano nicely in the distance through that window, which I really quite liked that image. So Merapi is a very big stratovolcano. We're about 8 to 9 kilometers distance here. It's also a very humid location to measure, which comes with its challenges for a range of different styles of behavior. It's also a particularly important place to measure sulfur dioxide emissions to understand the state of the system and to provide the potential to forecast activity. So here is Merapi. You can see here again these problems with clouds and spiders appearing and birds. This was a friend that appears every now and again in this particular imagery. But this really goes to highlight the issues with light dilution and cloud at this particular location. So light dilution is the effect whereby between the plume so where the point where you want to measure, and the camera, you're not directly measuring all of the light which has passed through the plume and then is measured directly by the camera system. Some of that light has been scattered in to the field of view. So you're not actually measuring you're not actually measuring that original signal. It's diluted. So that's the light dilution effect. And you can see that in action here. We've got this bird directly in front of the camera. It's very dark. Whereas the flanks of the volcano at about 8 kilometers away are very light. So that is the light dilution in action there. So we haven't yet attempted this at Merapi, but for some of the other locations, we've corrected for this effect. So here's some example data for Merapi. So this here is SO2 emission rate in tons per day on the left-hand side. This is non-light dilution corrected. We're somewhere between 50 and 150 to 200 tons per day in this data. And this is typical plot of what this imagery looks like. We've got the flanks of the volcano, we've got our integration lines, the plume speed, which is quite low at Merapi, and the plume here. So we can definitely reconcile it and get these measurements. This is from September 2023. This is all preliminary, I should add. This is kind of work in progress. So don't take these values as definitive. And here are some examples of this data, but I particularly want to draw your attention here now to the additional DOAS data. So this is co-located NOVAC instruments, so the network for observing volcanoes, and I forget what the acronym is off the top of my head. So many acronyms around the place. But this is a NOVAC network installation. They have 3 at different locations around the volcano to pick up when different plumes, different wind directions are transporting those plumes in different directions. So this is the perfect time to kind of demonstrate how they work in tandem. And this is an example of a day where we've got the 3 DOAS instruments, and they're probably not imaging the plume on these days. Whereas the UV camera it's got a nice perpendicular view, and we're getting a nice emission rate trace. And here's one of those collapse events where we see an uptick in that particular flow at that particular point. So this is kind of an example where the UV camera works really well in this instance. And obviously we have the vice versa as well. And here's an example of where they work really well together. So this is a little bit to unpack here. We'll start with the top left. So UV camera data allows us to get the real high time resolution emissions, but also the plume velocity from that. So this black line here is the plume velocity. We've got our median velocity about here. The blue dots over the top, these are modeled velocities, and often scanning spectrometers, not always, they will use modeled velocities, not the actual velocity. And you can see here the difference between the two. Initially, it matches quite well there, but later on, there is a bit of a difference between about, just over 2 and 1.2, which could have implications for the eventual emission rates you get out in tons per day or kilograms per second or whatever you do. And you can see this here on the right hand side. What we've done is I've kind of produced an interpolation of the Era 5 wind and correlated with that UV wind, and you can see there's no real link between the two at all in those instances. So you really need those actual wind speed values. This isn't me saying the DOAS data isn't usable. It is, it's really useful. What you can do is you can combine the two together. You could take the UV camera wind speed and correct the spectrometers with that wind speed. So this is what this plot is about here. A bit to break down. So the black trace is the UV camera. The circle is the original DOAS data for the 2 different sites, so one at Babadan and one at Draka around Merapi. and the bars are the plume completeness value. So how much of that plume the algorithm thinks it can seize. And the closer to 100%, the better, in essence. So we've got two sites which do see it. You can see the blue site doesn't see it. What we can do is we can take these original values and we can correct it. And these are those corrected Babadan, corrected Draka. And you shift these circle dots down a little bit, and you see something which is far more aligned and matching up together. So again, this is preliminary, but hopefully this is showing how these two instruments work together. They complement each other through time. And here, this is very poor practice, but just to illustrate how these two systems work together for all data. So plume completeness more than 0. So if there's a more than 0, I give it a dot, which might not be the case. And this is for a prolonged period, three months or so in 2003, between the red, which is DOAS at Babadan, the site which has the most frequent measurements in the period I looked, and the black measurements, the black box plots, which are our UV camera. And the important bit here is that they're kind of agreeing some of the time, but they're all in the same area. So you've got two kind of independent streams, which at the moment aren't talking to each other, and they're giving you roughly similar information about the broad amount of gas coming out of this system. And what we can do is we can take this and we can put it in a more readable plot. So here we have these box plots on the left-hand side for this period. We've both got 31 days of data between the Novak DOAS and the UV camera, and they're in the same range. The DOAS has got a slightly wider range, the UV camera a slightly narrower range, possibly because of light dilution. The DOAS shouldn't be susceptible to that because the plume is moving overhead, not very far overhead, whereas the UV camera is a further distance. Then you also balance that with the DOAS might have a higher plume speed than expected. But all in all, if you look at the right-hand plot, our emission rates in tons per day, apart from a few of the DOAS ones earlier on, it's all in the same region, which for forecasting purposes and understanding the state of the system is really reassuring. All in that kind of 100 ton per day region. So illustrating the complementary nature of those two techniques. As a bit of a side note, there were two domes at the time, and because we've got the spatial capability of the UV camera, albeit at distance, you can begin to reconcile some of the spatial differences between the two. So the flank dome has proportionally more gas coming out of it than the central dome on one of the particular days. But it's very difficult to reconcile those two because the plumes merged very quickly. So it was only, I think I only found a 30-minute period where it's possible to split them out reliably. So that's Merapi, and that's a really really excited about that case study because it's a real comparison of those two techniques, and I think demonstrating the complementarity and how they can really work together, not in isolation. I now want to talk a little about Kīlauea, and this is work that's currently in review at the Bulletin of Volcanology. This is probably our most successful camera setup so far. It's been installed since July 2022. We've seen 3 different phases of activity: low emissions, moderate emissions, and high emissions, and we've captured entire eruptions. So this is the kind of setup you see on the right hand side, the UV camera with its field of view at about 28 degrees, and this is a manual traverse, so the driven traverses underneath where the plume is, and you can see where the concentrations are highest within that plume, and that's pretty typical of those locations. Importantly, what we've also done here is corrected for the static light dilution effect using the algorithm of Matt Varnum, who I see is on this on the live viewing here, and I know we've spoken about this before, Matt, but this I'll leave kind of the details of that correction to that paper, as it does a really good job of it. But what it does is it's kind of looking at the ratios of different scattered in light, different wavelengths to work out the light dilution correction of the spectrometer. And if we correct the spectrometer, then we can use the imagery and the corrected spectrometer to produce a more accurate and light dilution accompanied correction of our data, so we get something which is closer to the truth. And bear in mind here that we're not that far away from the plume here. We're 2 or 3 kilometers, and the light dilution factor is on average about 0.22, something like that. So we incorporate a static because it's computationally quite expensive to do this more frequently, quite honestly. So we experimented with a static light dilution correction. And we initially attempted this on lava lake activity. So here's July and August 2022. And the red are the DOAS traverses and the ranges. The black are UV camera means and box plots of the range. And just bear in mind here that we're not really comparing like for like and time frames here necessarily, because you imagine the DOAS traverses maybe take place over 30 minutes to an hour. They might be 5 to 10 traverses, whereas the UV camera data could be up to 5,000 data points in a day. So you might be looking at different time frames, but in all instances we are matching up with the general emission rate values, but also within the varying ranges. So we're agreeing reasonably well, and again, this is completely independently speaking. We're not using any of the data from one to inform the other. They're two completely independent techniques. And again, just to highlight some of the interesting things you can get from it, something I've done in my previous work is look at patterns in data. And some of those I kind of previously identified as volcanic, but the more and more I look and think about it and compare those with geophysical data sets, the more likely it is that it's atmospheric. Not in every case, but here's an example of something which looks very pulsatory. You almost see this pulse and then a coda potentially in that emissions, but could it be atmospheric related to that very large crater you have at the summit of Kīlauea? So really useful for asking these questions. And this is, I'm not going to show this entire video, but this is the June 2023 eruption. And you can see here it starts, this what I call the plume of doom is almost entirely SO2 in this imagery. We're not capturing the whole thing. We then move on over different days, and you can see the plume reducing in size, and we're able to constrain the entirety of it within our imagery and get a more realistic gas emission rate through this. So there's a lot of days to get through in this data, but through time you can see the initial source moving. It becomes a little bit more point source as the fountaining reduces in size and reduces in strength, and you can see the equivalent happen to the plume here as well over this period of time. So what we can then do is we can then compare more traverses with our red against our UV camera in our black, the means and box plots. And again, you can see we're capturing this really nice trend. But note this time we've got log scale because of the very large emission rate, so between 200 and 300 kilograms per second. If you use that kind of framing of things initially, dropping to 50 to 100 kilograms per second as things progress. We're really capturing that exponential decay. And this large difference on the first day is because the SO2 is so much. We're having issues with the channels that we're measuring our SO2 absorption at in the UV camera, but also we're not capturing the entirety of that plume. So we're missing quite a bit of information. But again, this is a really kind of reassuring look at this particular data set. And again, we're capturing the same patterns, but also we can look at the spatial element to this, but also the temporal. So moving from kind of an overall, looking at all of the data to individual traverses and days, and you'll notice, let's start with the 8th of June, We've got some difference between the two. We're switching to kilograms per second instead of tons per day. We're in the same region, and the blue dots are predominantly matching up. So that's the DOAS individual traverses are matching up quite well with our UV camera derived data. The red is a moving average. And these are not speaking to each other at all. They're incorporating that static light dilution correction, and we're matching up incredibly well. And that's even more so for the 10th of June here, where you see this match up at about 10 o'clock. But note that there are only 6 data points there, whereas we have 8 hours of data with this UV camera imagery. So we know that volcanoes are dynamic things. Lava fountaining can wax and wane through time. The UV camera picks this up, but the DOAS traverse needs a human operator, where the UV camera doesn't. You might process the data. But yeah, hopefully this is a really nice illustration of UV camera data, DOAS traverses just beneath the plume, completely independent data, not speaking to each other at all, and we agree very, very well between the two. And then this is just to illustrate what the looks like can be with geophysical data sets. So this is SO2 emission rates in red this time, with a seismic root mean squared, just the vertical component, over a 1 minute window. And you can see the real link between these two, where as the seismic RMS declines, the energy of the eruption, so does the gas driving it. So these are kind of things which are really now derivable with the UV camera, which maybe wouldn't have been with the DOAS. 2 independent data streams telling you the same thing gives you more confidence in your interpretation of the activity and what it might be doing. And again, this is Kīlauea for September 2023, another eruption, kilograms per second, again a log scale, and you can see not a lot happening. The plume enters the imagery to show when the start of the eruption is, and I don't trust this data on the right hand side at all, because of the plume is not in the field of view and there's a lot of gas in it, but it really nicely highlights the lack of anything happening, anything noticeable happening before this particular eruption starts. And then just to round off the suite of emission scenarios here, where we have estimates to emission rates in tons per day between about 50 and 200 tons per day. And this is a period, if I recall correctly, where there were no traverses being conducted. Again, it requires person power, and you can just use your UV camera to check in and, okay, we're around the same tons per day. We don't need to go out and send out a verification with the traverse-based scenarios. And this is very similar to the levels seen at Merapi as well. So hopefully Kīlauea illustrates the real large suite and range of scenarios that can be imaged with a UV camera, from quiescent low emission scenarios through to high energy lava fountaining, albeit relatively ash-free events, because UV cameras and most spectroscopic techniques don't deal well with ash. So I want to finish off with this example here is Listaria. This is the kind of a case study volcano. It's got a nice prevailing wind direction. It's got lots of different fields. So this is 310 nanometer imagery again, where SO2 absorbs. You can see all these fields, and you can see field 1 on the far right hand side here. Now, sighting the UV camera here is a real challenge to pick up all of these different sources. If you pick up all of field 1, for instance, you lose the rest of them. You lose particularly field 2 and 4. So you have to kind of orientate this to capture all of field 2, 3, 4, and capture field 1 when you can see it within the field of view. And this is important for something I'm going to talk about in a little bit. So here's some example imagery. It is fantastic. It is the gold standard in my view for UV camera imagery. Nice coherent backgrounds, very clear visible plumes, great for deriving optical flow based plume speeds. And you can even begin to, this is just kind of a quick mock-up illustration of capturing spatial emissions from different vents. So the different vents here and an overall one, and you can even do the field one over this side. So you can see what these cross sections look like on this section here, where you've got 1, 2, 3, 4 key different sources. On this side, field one not included, and you can see what those profiles look like. 1, 2, 3, 4 match up with the colors. So you can see what we're kind of doing here. We're taking this very spatial information and we're trying to work out how much gas is coming out from each vent. Does that tell us anything about dynamics at this particular volcano? So again, we're working on light dilution corrections here. I'm doing a more rigorous day-by-day version instead of the quick computational average. And there's maybe suggestions that this is data between November 2022 and July 2023. It's a lot of work doing this. There's some suggestions that this is seasonal. So high light dilutions in the summer, in the southern hemisphere, compared to the winter in the summer hemisphere. And that will feed into the corrections, and maybe you're eliminating some seasonal pattern by correcting for light dilution function if you don't do this. So correcting seasonally is probably really important at a volcano like Listaria. And here's an example of one of those days, and I could bring up numerous examples of this, is that the mean fluxes at this location don't tell the full story. So here you've got all plumes measured. So when you've got all plumes measured, the mean is closer to 15, 16 kilograms per second. This is camera light dilution corrected and light dilution corrected and spectrometer light dilution corrected data. So we're reasonably confident it's looking quite near the real values given the quality of the data. However, when field one is missing or partially missing and it's out of the field of view, we drop our values significantly. So taking the mean at a location like Listaria, you're really missing the whole picture in this particular data set, in this particular instance. So is the amount of gas coming out closer to 16 rather than 8, for instance? So this is the mean of the means. So the mean of the means is around 7, and these are the means for each individual day processed. You can see the large number of days, and you can see that there's variation likely related to plume position for the most part, and how much we're capturing. I've yet to go through rigorous quality control for this, but it's kind of the first look, and we're pretty close to this region within error, with the odd higher value up here. So perhaps the mean isn't telling the whole story in this particular instance again. But what we can do, and this is data I've looked at, is look at different sources and different proportions. And this is possibly backing up the point I made earlier, in that field one makes up about 50% of the emissions. So if field one is missing from the data, you're 50% lower. And this is an attempt to kind of correct for this in various scenarios where you can see the emission rates are pretty close to high, and that when the field one is lower, you see that the overall emission rates, so these are the box plots in white, so that's the emission rates plus the interquartile range, the proportion of field one is lower. So when field one isn't visible, the emission rates are lower. And actually, we could use this to correct for the data to get a more reasonable look at what's going on. And my hypothesis here, not proven, a working hypothesis, working to test, is that actually the emission rates of this volcano are pretty stable, and that when you correct for all the different sources of error, things don't change much, bar and light a bit of noise and a bit of fluctuation within that. So that's kind of the working hypothesis there. But you can see the value of the UV camera here, where you can really work out the proportions from the different fields, work out what's contributing more. Does it change through time? Is it changing through time? What does that tell us about magma source, magma pathways, and so on? And if you imagine then combining that with gas ratio data to look at where this gas is coming from at depth through time, you've got an incredibly valuable data source. So the future of the star is pretty exciting. We've got Starlink telemetry installed. We use something called tail scale, so we can remote connect to the instrument via an Ethernet connection to the Starlink. We then transfer it to an online server with data automatically processed using our open source software. And this is kind of a trial and work in progress. But the goal being, you can go out, you can install a UV camera, and you can essentially plug and play. You put it in place, and you have everything software-based and hardware-based to just turn it on, put a few initial parameters in place, and away you go. So hopefully you found that an interesting insight into UV cameras, what they can do, and a flavour of some of the places we've got measurements. And hopefully we're going to start publishing some of this work too soon, so that we can kind of show you a little bit more about what we've been doing at different places. But hopefully I've illustrated that low-cost instrumentation provides greater access to data around more volcanoes. And the way to do this is really permanent systems to increase data chances, and that you need a different approach at each volcano. And what I want to really emphasize at this is not me giving a talk about why everyone should have UV cameras and they're the best and we should only use them. This is really they're complementary to existing techniques, whether that's DOAS scanning network, arrays, additions to give more information to gas sampling. Gas is really better when working as a kind of an ensemble approach with lots of different techniques. So UV cameras are a complement, and we should be using them more, as well as other bits of equipment. And a bit of a side project we're working on at the moment is commercializing this technology via the company VolcanoTech to really enhance access to this instrumentation to really work for the volcanic community. So that's what I want to talk about today. Thank you so much for listening, and hand over to back to Ben, I guess, for questions.
Cool. Thank you very much, Tom, for the really interesting talk. I haven't seen any questions in the chat yet, although I have about 17, so I could keep talking for the entire question and answer, but I'll try not to do that for the sake of the audience. But yeah, if anyone does have any questions, please pop them in the chat, in the Q&A, and we'll get them read out in there. Whilst we're waiting, I may jump in for the first one, if that's okay with everyone else. My first question was about the locations where you've installed these cameras. Mm-hmm. So obviously you had Kīlauea in Indonesia, but the rest of them are all Central and South America. And I guess my question is that intentional? Like, is there a specific thing you're trying to target there? Or is that like where the data is good? Or yeah, what's the reasoning behind that?
That's a really good question. And initially it's based on who was interested, to be quite honest. Often these collaborations have appeared because groups have got in contact with us and said, oh, we'd love to get a system. Can you help us install it? And it goes from there. So we haven't really done much targeted installation and reaching out to people directly. It's more people reaching out to us. We managed to secure some funding with various routes. We've done a lot of impact work, for instance, down that route. So yeah, predominantly it's people contacting us and us helping them to kind of learn more about UV cameras, process the data, and help them maintain it and monitor the system. But that tends to have been some groups we worked really well with and who are prolific users in South America.
Yeah. Cool, great. I may carry on with the second question unless anyone else wants to jump in. Yep. I was just wondering about a lot of the time series you showed. Obviously, you're using a smoothing factor to look at the sort of less high resolution variability. But it really struck me when you had the plot of the tremor versus the SO2 emissions, because they both seem to have the same sort of dynamic range in their variability. So I guess my question there is, do you think that variability is coming from true short-term variations in the SO2 emissions, or is that variability entirely coming from your wind speed estimation? That's just quite a variable signal in there.
That's certainly something I should probably investigate. My instinct says that the variability is almost certainly coming from, or probably, should we say, 60% certain, let's go with, from the actual gas itself. And that's because at these points, these fountains were quite high, so we're measuring at almost the point the gas is coming from that fountain at the top. It might be that that's partially plume speed, but then plume speed multiplied by the amount of gas coming out, you should still preserve some of that initial trend. And I'm not that much of a believer in coincidence. So if the data is showing the same patterns, then I should probably smooth it a little bit more and do some more comparison of it to really kind of investigate that in more detail. Then it's probably a linked process.
No, it's really cool. I think, yeah, a lot of times what you think might just be noise is when you pick it apart, you can find some really interesting sort of links and stuff. So that's very cool.
Yeah. If I was talking to my teaching stats, well, the eye is very good at seeing what it wants to see. So I always try and keep that in mind.
Yeah. No other questions coming in so far, so I may just finish off with one more. I'm really hogging this Q&A session.
There looks like there's one from Matt.
Oh, does it? Oh, new posts. There we go.
Yeah.
Sorry.
Yeah, no, you're good. Hold your last question, Ben.
Okay, I'll read it out for everyone then. Yeah. Hi Tom, thanks for the great talk, and I love the data from the star area. Thinking a bit about the complementarity you showed between DOAS and SO2 camera, which parameters for an SO2 emission rate measurements would you get from the camera versus DOAS, e.g. plume direction, wind speed, overall emission rate? Also, which parts of the measurements would you keep independent?
Yeah. So from the SO2 camera to feed into the DOAS, I'd take the wind speed. So that's predominantly what I'd take from the SO2 camera. For the DOAS, from the DOAS feeding into the SO2 camera, if possible, I'd take more information on plume direction. And by and large, I wouldn't communicate too much on integrated column amounts, but you could take information on plume height, for instance, from the UV camera, and where that might be transiting over the DOAS to get a more accurate plume heights. And maybe you could do a bit about plume dimensions as well to hone that down. But sharing too much data might not be beneficial, but you can certainly, the key ones would be wind speed, plume direction, plume heights, I think, as I think Matt mentioned.
Cool. I'm now keeping an eye for the new messages appearing thing, which I missed before, but I don't think there are any more. So one last one, if I may, which is how automated is the start to finish analysis that you have now? Is this all happening locally and then you just transmit the emission rates, or is there a lot of involved processing after the fact, as it were?
Yeah, we're getting there is the answer. Getting an open source approach to this with Python as the kind of the back end doing all the work is challenging, but the best way we've got of doing it so far, and it's pretty good if the data is good. The moment the data is a little bit beyond good, it becomes a bit more challenging. But the way we do things now is we take all the data. We will process the spectrometer data first, and so it's usually processed in the evening. The spectrometer data will process. We'll then process the imagery alongside the calibrated data in the evening, and then you'll get a kind of a flux trace and statistics for the next morning. So it's overnight processing for the next day. We really tried with real-time emissions on a kind of a minute-by-minute basis, but it was too much. And actually, the halfway houses process it all overnight, and you get your readings the next day.
Cool. Thank you very much. So one last question from Alex here. Thanks for the great talk. Have you ever tried any tomography with multiple SO2 cameras to look at plume dynamics and transport?
No, it sounds very complicated, and it sounds like a whole PhD of work or a postdoc, something like that. It would be really interesting, for sure, to look at plume dynamics, but no, unfortunately not tried it.
guess could at least something for the future.
Yes.
Cool. I think with that then we'll probably bring to a close unless any other questions pop up. So just to say thank you to Tom again for today's webinar, and thank you everyone for attending. A quick reminder for next month's, please stop me if I'm going to go wrong here, someone, but on the 21st of May we have John Elliott from Leeds. We'll be talking about Alpine Himalayan belt INSAR. So keep an eye out for the advert for that, and that should be coming out shortly. Is there anything else I need to mention, Jin and Aaron? All good. Perfect. Okay. In that case, thank you very much, everyone, again, and we'll see you next time.
Thank you all.